Hello everyone. In this lecture, I'm going to talk about atomic force microscopy. So its principal modes of operation and measurement of surface roughness. So AFM belongs to the family of scanning probe microscopy. So based on the principle that a sharp probe scans over a sample surface to construct a three-dimensional surface topography. So it all started with the invention of scanning tunneling microscopy. So in 1981 by Binning and Roher at IBM Zurich, for which they won the Nobel Prize at 1986. So the principle of STM is that electrons quantum mechanically tunneling between an atomically sharp conducting tip and the sample surface. The tunneling current varies exponentially with the distance. So this exponential dependence makes it the device very sensitive to the slight change in height experienced as the tip moves across the surface. Okay, so the tip of the STM is usually made up of tungsten or platinum iridium, so usually obtained by electrochemical etching. So it's usually the tip is just one atom. The vertical resolution of STM is up to 0.01 nanometer. So a single atom can be resolved, and the lateral resolution is up to zero point 0.1 nanometer. So only the limitation of this STM is that you can only use the conductive samples. So to overcome this, in 1986, atomic force microscope was invented. So in this AFM, a cantilever with a known spring constant, in which it consists of a sharp tip at the end, is mounted over the sample surface, and which is actually attached to the piezoelectric scanners. The cantilever deflects by an amount which is proportional to the force, usually measured by an optical detection method. The cantilever is made up of usually silicon or silicon nitride material, and the radius of tip is usually less than 10 nanometer. So there are mainly three different modes of operation to use the AFM. So one is the contact mode, the other the non-contact mode, and the third one is tapping or intermediate contact mode. So to understand how these three different mode works, so let's simply take the Liouville-Jones potential. So if you have plot the potential against the distance, so the AFM, the contact mode AFM actually works in the repulsive interaction region. The non-contact mode works in the attractive region. And the intermediate contact mode, which actually oscillates between these two regions. So in the contact mode, the cantilever is always in contact with the sample surface. So a strong repulsive force causes the cantilever to deflect when it's scanned over the sample surface. Okay, here the deflection or the force is kept constant using the feedback loop, so which moves the Z scanner to move up or down, which represents the topography of the sample. So here the contact mode actually can have a destructive effects on tip or sample, depending upon the force you apply on the sample. For example, if you have a hard surface, usually you can image quite nicely with the contact mode. For example, here a silicon surface. But if you have a relatively soft sample, here human hair, which reveals the steps here, you can also see here that the edges of the steps are damaged during the back and forth scanning with the contact mode. But this is still okay, not so bad. But if you, for example, use a very soft sample, like for example here a polymer brush coated on a silicon surface. So if you use, for example, a scan using contact mode, and here it's scanned 3 micron area, and later you check with the tapping mode, larger area, and you can see how much your sample was destroyed during the contact mode imaging. So apart from this destructive effect of contact mode, so you can also use this to measure the friction between the tip and the sample, so which is often known as friction force microscopy or lateral force microscopy. So if you just look at the photo detector, so which usually has 4 quadrant A, B, C, D. So the information which you get from the difference between the upper two um, quadrant of the detector gives the topographical information, which is the vertical deflection, whereas the signal with the other two side of the photodetector gives the information on the lateral twist in the cantilever due to the friction. So when you back and forth scan the cantilever across the sample, so you get kind of loop which is often known as a friction loop. So it's a trace and retrace. So it's blue is in scanning in one direction and the red is in the other direction. So the area between this loop between trace and retrace which gives you the information about the energy dissipated due to the friction. So in this study, for example, how you can use this friction force microscopy to characterize different surfaces. So here a polymer brush coated on silicon surface which varies the length across the sample. So to understand how this polymer chain length affects on the frictional property, so we just scanned here in a small area on each location of this sample. Here you can characterize how the polymer chain length affects on the friction force. For example, here the shorter the chain, so you have lesser friction. However, the longer chain, the friction increases. So another mode is a non-contact AFM mode. So here the cantilever oscillates slightly above the surface, so which relies on the weak attractive force in the region before the contact occurs. So the oscillation amplitude here is kept constant using the feedback loop, unlike in contact mode where the deflection was kept constant. So which moves the Z scanner up or down depending upon the topography. So this non-contact mode is very rarely used because it relies on the weak attractive forces and it's very sensitive to the thermal effects. The most widely used mode of operation is tapping mode or intermediate contact mode. Here, the cantilever is in contact intermediately with the surface, so which actually taps near to the resonant frequency of the cantilever, and the amplitude of oscillation here is much higher than that of non-contact mode. So here the cantilever actually touches, but on and off, gently touches the surface. So and the amplitude of the oscillation is kept constant by using the feedback. And this mode is more commonly used for even imaging in dry as well as in liquid. For example, here even the soft sample here a single DNA strand can be imaged in liquid by using this tapping mode. So apart from just imaging, so you can also use this AFM to measure the forces between the tip and the sample, as well as you can obtain some material properties, for example, elastic property of the sample surface, so which is commonly known as a force distance measurement. So how you obtain this force distance curve? You just ramp the Z piezo. So for example, initially a tip is far away from the surface. So by moving the piezo closer, the tip comes closer to the surface, and due to the attractive interaction, it usually jumps into the contact. And after this, if you still move the Z piezo, so you actually press, or if the sample is soft, you indent into the sample surface, and at some point you start to retract So you come back from the surface. So during this retraction process, the tip strongly adhere to the sample surface. So when you move away the piezo, so then it comes back to its original position, so which is a measure of adhesion between the tip and the sample. So from the slope of the curve between B and C, um, the information about the elastic property of the sample can be obtained, because here you are actually indenting and deforming the sample, so you can get the elastic property of the sample. The region E, which gives the information about the adhesion between the tip and the sample. For example, in this study, we have a polynipalm brushes, which are coated on silicon surface. So these brushes are very soft polymer chines, and at 25 degree in water they swell and they are really smooth and soft. So you can see in the topography at 40 degree, actually they dehydrate, the water comes out from these chines, and then they form a kind of cluster on the surface. So if you look at the force versus distance curve, so at 25 degree it shows highly repulsive interaction, so there is no adhesion because of the chines are stretched from the surface. However, at 40 degree you can see the adhesion because it's dehydrated. Okay, also from by fitting this region of the curves, you can extract the elastic modulus, so here by using the Hart's equation. So as you can see here at 25 degree, it is relatively soft, and at 40 degree the elastic modulus increases an order magnitude higher. Apart from using the AFM for imaging and also for measuring elastic property and adhesion properties, so it's also extensively used for surface roughness analysis, as this is the only technique offering unparalleled three-dimensional spatial resolution, and also for its ability to measure most of the material in ambient condition as well as in the liquid environment. So roughness plays an important role when two surfaces come into contact. So roughness is often a good predictor of the performance of many mechanical components. So most real surfaces can have roughness over many length scales. So even when two thoroughly polished surfaces, you can call it as a nominally flat surface, come into contact due to the existence of the micro or nanoscale roughness, the actual contact occurs only at the discrete points or asperities. So for example, if you bring two surfaces, nominally flat surfaces, into contact, means a situation is like you are bringing a Swiss Alp on top of an Austrian Alps. That means the contact occurs only along a few asperities, which effectively lowers the area of contact. So this surface roughness is an important parameter that affects the tribological behavior of surfaces. For example, asperities interlacking or deformation can increase friction, or eventually can end up having higher wear at the surface. So this roughness and understanding of this roughness, how this affects on adhesion and friction, plays an important role in many areas of science and engineering. For example, in micro electromechanical system and nano electromechanical system, as well as in bio interfaces, where control of adhesion on implant surfaces are very crucial. Also the automobiles, wherein a friction of engine as well as rubber friction, where the roughness plays an important role. Also in adhesives, as well as in micro nano robotics, where the roughness of surface play an important role here in the locomotion of the micro nano robots. For example, if you just rub your finger over different surfaces, you feel different resistance, right? So which can be correlated to grip of your hand on different materials. So in this study, for example, the friction between the finger and different surfaces are studied. So initially, if the roughness is low, the friction linearly increases with the roughness. So after reaching a threshold, the roughness doesn't play any role. So this is probably due to the at lower roughness of the sample, you probably matching the roughness of the substrate with the roughness of your finger. So there are many roughness parameters, but for most of surfaces, the RMS and the average roughness, which is quite often used, and also other roughness values, RT, RP, and RZ, which is also quite often used. So they are all the amplitude roughness parameters where the lateral variation of the topography are ignored. So, but you can have surfaces which has same RMS values but can have a different structure and can effectively have a different contact areas when you bring these two surfaces into contact. So these kind of surfaces can be best described using slope or a spacing parameters. For example, in this study here, a nanoparticles which has the same height deposited on a silicon surface. So what varies here is just the density. The roughness is defined as the particle density. So the pull-up force or adhesion here measured by AFM, which shows that the adhesion is directly proportional to the number of contacts. So more number of particles come into the contact will have a higher adhesion. Okay, also the friction, which shows the similar result, that the more number of particles come into contact has higher contact area and higher friction. So by the way, here is just instead of a sharp tip here, a big collide is used just to have a larger contact area. So how we measure the surface roughness by using AFM? It's quite straightforward. So first, capture a clean, noise-free image by using contact or tapping mode AFM. Depends upon your sample, which suits best for you. So I hope you watched the video to learn how to acquire a contact mode AFM image. Once you acquire an image, so you do basic leveling of the sample to correct the tilt during the measurement, and you can just obtain the roughness by taking a cross section or get a roughness value for the entire scanned area by using the image analysis. So here we showed by using the Gaussian image analysis software. Yeah, so it's just you drag a line and then you can you can extract the RA and RQ and other roughness parameters, or you, as I said, you can just extract the statistical quantities which gives the roughness values over the entire scanned region. So that's all about this lecture. So in summary, I hope you learned a little bit about AFM and the principle of AFM, the modes of operation, as well as acquiring force curve and how you can use this force curve to extract the adhesion as well as elastic property of the sample. So at the end, I assume that you learned about surface roughness, different kinds of surface roughness, and how you can extract the roughness parameters from the acquired AFM image. So I thank you all for listening.